Okay. Howdy. Good afternoon. Any questions, comments about last Monday, the exam? I think most of you were able to finish the exam at the time. There were some of you who stayed up to the end, for about 10 students. So most of you were able to finish it in an hour, which was what I was expecting. So for the exam, I have the grades. So I'm going to return the papers at the end of the lecture. So around 3:05, please let me know. I'm going to stop the lecture, and I'm going to return the papers. So that's for the exam. Today, we're going to start with new material. Still on chapter 3 of your textbook, and we're still talking about random variables and probability distributions. Okay? So this is the material that is going to be included in your second exam. From now on, is material for the second exam. Okay? So before I get started, I need to ask another question that I've been asking a couple of times in the class. What is a random variable? And it was part of the exam. And I think half of you were able to answer it, but half of you still don't know what is a random variable. You do know what is the difference between discrete and continuous, which was kind of difficult for me to understand because you know what is the difference, but you don't know what a random variable is. So does anyone remember what is a random variable? And the funny thing is, some of you asked me what type of question you should expect in the exam, and I think that was the question I asked, right? So if you were paying attention, I told you the question was what was going to ask in class. Well, anyway, a random variable is a function. It's a function that allocates a numerical description or value to one of the outcomes of your sample space. So if you have a sample space, let's say true or false, and you give a value of 1 to true and the value of 0 to false, that's your random variable, 1 and 0. Okay? So I want you to have that concept clear. So that's what a random variable means. Okay? You're assigning a value to one of the outcomes of your sample space. Okay? Okay. So from there, we're going to start today. I'm going to do the same thing I did a couple of weeks ago. I want you to be clear on how the material we're covering in class relates to what we're going to cover today. Okay, so let me draw. Oops, what's going on? So let's start by starting with defining what a sample is. At this point, you should know what is a sample. Sample contains all your outcomes for your experiments, right? So we start from there. Then we define what is an event. And an event is a subsample of your sample space. So it's part of the sample space. Then we talk about counting samples, counting sample points. Right? And we define some methods for this. From there, we started discussing how to get the probability of an event. And from there, do you remember what was the next topic we covered? I just mentioned it. Random variables. Okay, so there's a couple of relationships here. So sample relates to counting sample space, and the event to the probability of an event, and also the sample relates to random variables. So we assign numbers or values. It's a function that assigns numbers or values to your outcomes in the sample space. Then from there, the last thing we discussed in class was probability distributions. And we know that we have distributions that are discrete, which are based on random variables that are discrete. And we also have probability distribution for continuous random variables. So probability distributions, and we have discrete and continuous. Right? And that's the material at this point of the semester that you should know. Today, we're going to extend this a little bit. We're going to talk about other type of distributions, which are discrete or continuous, and those are joint. So we're going to talk about joint discrete distributions and joint continuous distributions. Okay? And that's the topic for today. We're going to define what a joint distribution is and how we're going to use joint distributions in this class. Okay? So are we clear where we are at this point of the semester? What we're trying to do now is going to extend the knowledge we have about distributions to joint distributions in both cases, discrete and continuous. Okay? So we're still in chapter 3. And the topic we're covering today is joint probability distributions. And basically, you need to know that some variables are not independent of each other. They tend to be related somehow. For example, urban vehicle speeds and fuel consumption rates tend to vary inversely. So the more you drive, the more fuel consumption rates, or if you ride your vehicle at higher speed, you know that your fuel consumption is going to be higher. Also, this is an example that I'm trying to present here because there was a question in class about what is an injection molding. So this is an example that relates to that. The length of the injection mold part might not be independent of the width. When I refer to injection molding, is the style process or manufacturing process in which you're trying to create a part using mold. Okay, so you have this equipment that basically injects the material, and you're trying to give that form based on the mold. Okay, so the length and the width of the part may vary depending on each other. So a joint probability distribution will describe the behavior of several random variables, say x and y. So what we're trying to model now is if there's an effect of one variable into the other, how are they related and how to model that. Another example, let's say you use your cell phone to check your airline reservation. The airline system requires that you speak the name of your departure city to the voice recognition system. And I hate this type of system, in which you have to basically tell the machine what you want to do. They prefer the system in which you can dial or something like that. But let's say you're looking at these type of systems, okay? Let Y denote the number of times that you have to stay in your departure city, and let X denote the number of bars of signal strength of your cell phone. So you know that the better reception, the better signal that you have in your cell phone, the better communication you will have with the system. Okay? So that's what we're trying to show here in this table. So essentially, we have a variable that denotes the number of bars of signal. Let's say you have 1, 2, and 3. And you have another variable that basically represents the number of times that you have to repeat the name of the city where you're going to travel. So, any ideas of what this is showing, these probabilities?
The worse the signal, the more time.
Exactly. So, the better the signal, let's say you have 3 bars, you'll see that the number of times that you really need to repeat the name of the city is going to be small. But if you have a bad reception, for instance, you have only 1 bar, then the probability is going to be higher for the number of times that you're going to have to repeat the city. Okay? And that's the thing that's what we're trying to represent here with the table as well. Okay? So if you have 3 bars, you know that the probability of repeating the city is going to be high. Only 1 is going to be higher. But when you start going to the number of cells or bars for your cell phone, let's say you only have 1, then you're going to have a higher bar here that denotes the number of times for repeating the city is going to be 4. Yes, sir.
So this data ends at 0.15. If you look at the 1 number of bars and 4 and 1, it ends at 0.15. Is that saying that most of your probability actually exists outside of this?
Just put 1 bar at 4 times, or state the name 4 times with 1 bar.
This is basically saying that if you only have 1 bar, you're going to have a higher probability of repeating the name of the city.
Yeah, but what it looks like to me is that you could probably put 5, 6, 7, 8, 9 down here, and it would increase.
Oh yeah, this is just a snapshot of the problem or example, basically. Yeah, you can get up to 1 here when you add these probabilities, and also up to 1 and up to 1.
Okay.
Okay, good question. Okay, so this is just a snapshot of the table, basically. So, and what I'm trying to represent here is just the idea that you see that these 2 variables are related and how the probabilities of those events happening relates. Okay? So this is the concept of joint probability. Okay, so now we're gonna basically focus on the 2 cases. First one, discrete case, then we're gonna transition to the continuous case. So for the discrete case, if x and y are 2 discrete random variables, the probability distribution for their simultaneous occurrence can be represented by a function with values f of x and y. And this is a function of both variables. Okay, so remember the probability distributions for discrete variables, we represented that as f of x. Now we are looking at 2 variables, so we have a function of 2 variables, x and y. For any pair of values, x and y, within the range of the random variable x and y. So we're going to have ranges for each variable, and we're going to have a function defined for those ranges. It is customary to refer to this function as the joint probability distribution of x and y. And for the discrete case, this is what we have. So the joint probability distribution basically looks at the probability of having the random variable x equals a number, and the random variable y equals a particular outcome or number. Okay? So that is the values of the function give the probability that the outcomes x and y occur at the same time. Okay? So we are looking at the discrete case, and we are trying to find the probability that both of those outcomes, x and y, occur at the same time. Go back. Can I move to the next slide? Okay. So this is a formal definition from your textbook, definition 3.8. The function f of x and y is a joint probability distribution or probability mass function of discrete random variable x and y if, remember the 3 conditions for the discrete probability distribution? What we're trying to do here is to extend that same definition to the joint probability distribution. So again, function now of 2 variables, x and y, needs to be greater or equal to 0. The sum of the probabilities for x and y needs to be equal to 1. And if you want to find the probability for a particular region, then you need to look at the summation for the ranges that you're going to have for X and Y. So we're going to sum those probabilities for X and Y. Do you remember what we used to do for continuous? To get the probability? The integral, right? So based on this definition, what are you going to be doing for the continuous? The double integral. Okay, so you better try to go back to your calculus textbook, or if you don't remember how to do that double integrals, because we're going to use that. Okay, this is the formal definition stated for joint probability distributions. Discrete case. Okay, so let's look at this example. And here we have 2 ballpoint pens and are selected at random from a box that contains 3 blue pens, 2 red pens, and 3 green pens. Then we define a variable x, which is the number of blue pens selected, and we also have y, which is the number of red pens selected. And I want you to find the probability function f of x and y. So let me write here, we have x, which represents the blue, and we have 3, and y represents red, and we have 2. Okay, and we need to pick 2 from the number of pens that we have. Okay, so the number or possible values pairs x and y are the following. We can have 0 and 0 for each random variable. We can have 0 and 1. We can have 1 and 0. We can have 1 and 1. We can have 0 and 2. And we can have 2 and 0. So those are the options that we have, or the outcomes that we can have for this experiment. Remember, 3 blue, 2 red, and we are trying to pick 2 from the box and see how many we have for reds and blue. So those are the outcomes for this experiment. Now, to get the joint probability, let's see, A, what would be the total number of equally likely ways of selecting any 2 pens from 8? How many combinations for selecting 2 out of 8? Correct. So the total number of equally likely ways of selecting any 2 pens from 8 equals this, which is equal to 28. Okay, so that's the total number of combinations that you can create with the number of options that you have. Okay, so using that, remember what we're trying to find here is the probability function. So we are looking at probabilities. So let's take one of the examples. So let's say we look at the function of 0 and 1. That means that you have 0 blue and 1 red. Okay, and that also means that you have 1 green. But we are not counting the number of green. So we have 0 blue, 1 red. Okay, so let me put that here. So 1 green. So the number of ways of selecting 1 red and 1 green, how can you compute that? Using the multiplication rule, right? So you can select 1 from 2 and 3 from 1. So that means that you have 6 options. So what will be f of 0, 1? F of 0, 1 will be 6 over 28, which is 3 over 14. So you're dividing the number of combinations that you can create, which we found here, and what will be the number of combinations that you can have for the specific result. And that will be the probability of that event to happen. We can do this or repeat this process for each of the pairs, or 0, 0, 0, 1, 1, 0, 1, 1, 0, 2, 2, 0. But I think you can basically understand what we're trying to do. So we are trying to build a probability function which consider 2 random variables, x and y, and we're trying to identify the probability of each outcome to happen. So we did an example just for 0 and 1, which is this case. Now, the process can be repeated, and basically, you can create something like this. So, in this table, we have f of x, y, for x and y. We have the outcomes for x, 0, 1, and 2, the outcomes for y, 0, 1, and 2, and the probability that we just found is for this case, f of 0 and 1. If you repeat the process for each one of the combinations, then you should be able to get 3 over 28 for 0, 0, 9 over 28 for 1, 0, and so on. Okay? So these are the probabilities for each independent outcome. Okay? And you can.
I'm sorry, I know that you have said that x and y could have the reverse function, x and y. X 0, y 0.
Yes,
It's saying that the probability to be 3.8 is
3 over 28.
yeah, but the row time alright. So basically just is that a numeric value or is that
This
okay, just a breakdown?
this is the probability.
No. 0, 0.
0, 0 means that you have 0 blue and 0 red. Okay? That's what that means. Okay? These 2 and 2 means that you have 0 probability of getting 2 and 2. Which makes sense because you're only taking 2. Okay? If you so that's basically how you get the probability for each outcome of the joint probability distribution. Okay? Then we're going to talk about this later in this lecture. We're going to talk about this number, which represents something else. Okay? So, in general, we can create or basically try to generate a generic expression or formula to get the probability for each outcome combination, x and y. And that you can represent the joint probability distribution with the following formula. F x y will be equal to 3 2y, and 3, 2 minus x minus y, divided by 8 over 2. So if you plot each one of the cases for x and y in this expression, you should be able to get the probabilities for the table.
You put so on.
What was that?
You put so on.
This note? Yeah, I can post it.
So what's the other part?
This one? So this basically says if you're, let's say you have 1 and 1 here, this will cancel out. That means that you have no, for that particular one,
Until you
it's
get to 0.
Yeah. Okay. Okay. So we have part B, P, X, Y. So we are looking at the probability that X and Y is in this particular subset or event A, where A is the region X and Y, where X plus Y is less than or equal to 1. So what I'm saying now is the summation of X and Y has to be less than 1, less than or equal to 1. So let's look at that particular case. Let me try to solve part B here. So the probability is the following. We are looking at the probability of X plus Y be less than or equal to 1. And when is that happening? Correct. So that only happens when you have 0, 0 for X and Y. You have 1 for X and 0 for Y. Or you have 0 for X and 1 for Y. I think that's what I said. Okay, so you have only 3 cases in which you can have X plus Y less than or equal to 1. When X equals 1 and Y equals 0, and Y equals 0 and X equals 1, and when both of them are 0. Remember, you're referring X and Y are the values of the random variable. So we have f of 0, 0, f of 0, 1, and f of 1, 0. Those are the only cases in which you can have X plus Y less than or equal to 1. And if you sum those probabilities, you have 3 over 28 plus 3 over 14 plus 9 over 28. That will equal 9 over 14. Any questions? Okay. I just wanted to say this one more time. This course, I would say, is not hard in terms of the material we cover. The difficulties about this class is that you need to have a different mindset. So it's like you need to look at things from a different perspective of what you're used to. So the best thing to understand this concept and how this math works is to go and repeat the process and try to solve the problem by yourself so you can get the mindset and the type of problems that we are trying to solve and how we solve them. Okay? So take a look again and let me know if you have questions. So let's transition to the continuous case. So for the continuous case, when X and Y are continuous random variables, the joint density function f of X and Y is the surface lying above the X and Y plane. So now we're looking at the 3D, basically a 3D environment. So now we're going to be integrating for x and y, and the area we are looking at is this area under the curve. Okay? So the probability that x and y is in the region A is determined by the volume of the function x and y over the region A, which is determined by x and y. So region A is this square, or that square, and we're looking at the volume for that area. Okay? So remember, initially we looked at only one variable. We were integrating for just x and y. We're looking at the area under the curve for the probability density function. Now we are looking at the combination of two random variables, which are continuous, and we are going to an additional cases in the area, and we are looking at the volume, not the area. Okay, so that's for joint probability distributions, and as you already mentioned, instead of using just the integral, we're going to use the double integral to get that probability. Okay, so continuous case, the formal definition from your textbook, the function is f of x and y. It's a joint density function of the continuous random variable x and y if same condition we have for the discrete case, the function has to be greater or equal to 0 for all the outcomes. The double integral of the function for x and y has to be equal to 1. Basically tells you that the probability for that function, for the two variables, the probability is equal to 1. Okay? And the last one, basically, to find the probability of x and y being in this bent space, you need to look at double integral for the region of the event, A. Okay? So let's try to look at one example and see what this example is about. So we have a business that operates both a drive-in facility and a walk-in facility. And on a random selected day, let x and y respectively be proportions of the time that the drive-in and the walk-in facilities are in use. So we're looking at the utilization of these facilities, walk-in and the drive-in. So let's say we're looking at the bank. And suppose that the joint density function of these random variables is given by this function, f of x of y, for this x between 0 and 1, and y between 0 and 1, and 0 elsewhere. Okay? So the first thing we need to do is to verify condition number 2 from definition. So essentially what we're trying to find out is that the sum of the probabilities equals 1. So you're going to integrate or double integrate for these ranges, x and y, this function. Let's look at that. So verify condition number 2. So we have the integral first. Let me write the definition. So this is by definition. This is going to be equal to the integral from minus infinity to infinity, minus infinity to infinity of the function x, y, dx, dy, and that has to be equal to 1. Okay? So that's condition number 2. So we're going to do that for this problem. So the first integral will go from 0 to 1. Right? Anybody knows why? Yes, because of the range. So we go from 0 to 1, and that's for y. Then we go from 0 to 1 for x, and we look at f. Let me write the actual function. So we have 2 over 5, 2x plus 3y with respect to x and with respect to y. Okay, so that's the expression that we need to solve. The function comes from here, the ranges come from here, and now we're looking at that probability. And what should be the result? 1. If it is 1, then we satisfy the condition of being a probability density function for both variables. Okay, so if we solve this, 0 to 1, the integral 2x squared over 5 plus 6xy over 5 for x equals 1 and x equals 0 dy. So if you solve this, then you get the second integration from 0 to 1, 2 over 5 plus 6y over 5 dy, and this is equal to 2y over 5 plus 3y squared divided by 5 from 0 to 1. So at the end you have 2 over 5 plus 3 over 5, which is equal to 1. So when you solve this double integral, you get that the probability equals 1. So we satisfy the condition number 2 of definition 3.1. Okay, and this definition basically states the properties for having a joint probability density function for a continuous random variable. Okay, so this is telling you that this is a joint probability density function. So now you can use it to find other probabilities. So part B is asking, find the probability of x and y being in this subset or event A, where A is equal to x being within 0 and 1/2, and y is between 1/4 and 1/2. We need to find that probability. Any ideas of how to get that? Double integral of the function 2x plus 3y for those limits. So can I move to the next slide? Everybody ready? Wait a little bit. So what is the meaning of A in this part B? What does A represent? What's that? Yes, is the area, and what the area represents? A is, remember, this is, say we go back to this, to the example of, let's say, 0 and 1. So this is your sample space, 0 and 1. Remember? If I define a subset of this sample space, we call that an event, right? So I can say A is an event of the sample space, and A is 0. So what I'm saying here, A is an event, and I'm trying to find what is the probability of that event. A is an event, is a sub-sample of the sample space. Okay, so that's what A means. So in this case, the event is the following. We are trying to find the event of x and y being within these limits. That's the event. Okay? So let's find that. So the probability of x and y being here, A, then that's equal to the probability of being within x between these limits and y between these limits. Okay, and remember these variables are representing time. So actually it is the time that we use both facilities. So these numbers, these variables, what they're saying is what is the probability that you use that facility, walking facility, which is x, right? No, x is the driving and y is the walking. So what is the probability that you use the driving x for half of it, for example? And the probability that you use the walking facility from 1/4, so let's say that's 10 in the morning to 2 in the afternoon. Okay, so that's what the type of, and you want to know the joint. What is the probability that both events happen? Okay, so let's solve this. 1/4 to 1/2 from 0 to 1/2, 2/5, 2x plus 3y, dx dy. And I think you should be able to solve this on your own. So I'm not going to perform the whole integration. I'm just going to give you the answer. So that probability will be 13/160. Are we clear? So we show how to find the joint probability for discrete probability distributions. We found the joint probability for continuous probability distributions. Are there any questions? We are doing the same thing. The only thing that for discrete, we use summations. For continuous, we use integration. Okay, so the next stop.
We have to do a lot of
Well, for these problems, you need to go with
because when I was in Cal 2 and I was in different rotations, I don't know, calculation.
Okay, but as I mentioned last week, I think I'm not gonna evaluate you in terms of your math. What I want to see is if you are able to express the right expression. So you need to be able to write this. If you're not able to get to this number, I can see the expression, so I know that you are doing things correctly. This is math. So for the purpose of the class, I just want to be sure that you know how to get the right expression for the probability case. This you can get using a calculator or a computer. Okay? So I'm not evaluating your calculus. Should know that by now. I'm evaluating you for the material of the class. Okay? So let's move to the next topic. Okay, so now remember what I mentioned that we were going to talk about those columns and rows in the table from the first example we discussed. Now we're going to touch on that, and we are discussing what our marginal distributions are. Okay, so given the joint probability distribution for f of two variables, x and y, of the discrete random variables x and y, the probability distribution of, or the function of x, alone is obtained by summing f of x and y over the values of y. So if you want to find out what are the values of x for this joint distribution, you know that both variables are dependent, but just you are interested in knowing just what are the values for x, you can look at the marginal distribution and find out what are the probabilities with respect to x. Okay? So you do that for x, summing over the values of y, and you can do the same thing for y, summing over the values of x. Okay? So we define x, or the function of x, and the function of y to be marginal distributions of x and y respectively. When these variables, x and y, are continuous, then the summations are replaced by what? Intervals. Okay. So we sum for the discrete, we integrate for the continuous. Okay, so there are marginal distributions for each random variable, formed by summing joint probability mass function over the other variable. So in this case, we are looking at discrete random variables. So remember how we name the probability distributions for the discrete case? They are probability mass functions. For the continuous case, they are named probability density functions. So PMF here means probability mass function over the other variables. So in the discrete case, we are looking at the summations. So let's say we are looking at the probabilities just for x. So you're going to find the probabilities for x by the summation of the values with respect to x, for the function. And the same thing for y, you sum with respect to x. So using an example here, let's look at this example, first example we discussed in class. So if you want to find the probability of x being equal to 1, how do you find that? You sum those probabilities with respect to y. So this is 1, 1, 1, 2, 1, 3, and 1, 4. And that probability for x equals 1 is 0.20. That's your marginal distribution. That's your marginal probability for x equals 1. You can repeat the process for x equals 2. You sum for x equals 2, you sum with respect to y. So x2 y1 0.2, x2 y2 0.03, x2 y3 0.10, and so on. You get the probability for x equals 2 is 0.25. You can do the process, same process for y. So for y, you need to sum with respect to x. So what you do is y equals 1, with respect to x equals 1, 0.01, with respect to x equals 2 and equals 3, you get the probability, which is 0.28. Those are the marginal distributions based on the joint probability distribution. Is that clear? Yes, that's a good question. So those marginal distributions, when you sum them, they need to be equal to 1. About the data? So essentially you're basically starting from the point that you have a joint distribution. The effect of having two variables and how are they related, right? So you start from that point. Now you want to get more information about the variables independent. So for that case, you need to use marginal probability. So you want to know more about the effect of x. What is the effect of x equals 1 to the probability? How you see from here, you can say that x equals b has more weight because it has a higher probability, and so on. Any other question? Okay, so that's for discrete. What I have next is the definition. So marginal distributions of x log and y log. For the discrete case, you have the summation with respect to y for the function of x, and the summation with respect to x for the variable y. Now, for the case in which you have continuous variables, then you need to look at the integral. For the case for function x, you look at the integration with respect to y. For function y, you look at the integration for x, with respect to x. Okay? Next, we have, I think it's basically what we just discussed, so let's go over that again. For this example, so let's say, show that the column and rows totals in this table give the marginal distribution of x alone and y alone. So let's do x. So g of x will be equal to the summation of y for function of f of x and y. So remember, this is discrete. This is a discrete distribution. So let's look at g of 0. So for that we have f of 0, 0 plus f of 0, 1 plus f of 0, 2. Right? Because we are summing with respect to y. So the number that should be changing are those related to y. We have y from 0 to 2. We sum from 0 to 2 with respect to y. And this is equal to 2 over 28 plus 3 over 14 plus 1 over 28. So this is 5 over 14, which is this number. For g of 1, we do f of 1, 0 plus f of 1, 1 plus f of 1, 2. So we have 9 over 28 plus 3 over 14 plus 0. So this is 15 over 28. And for the last one, for x equals 2, we have f of 2, 0 plus f of 2, 1 plus f of 2 and 2. And this equals 3 over 28 plus 0 plus 0. 3 over 28, which is this value. And the summation equals 1. So you can repeat the process for y, but in order to get the marginal distribution of y alone, you have to sum with respect to x, so you're going to be looking at these numbers, these rows. Okay? Does that make sense? Okay, so these are marginal distributions for discrete random variables. Let's look at one example in which you look at continuous random variables, which is the next problem. Can I move to the next slide? Just wait for 1 minute. So in the case of having a continuous or joint density function, we look at the integral. Okay, so let's find g of x and h of y for the joint density function that is represented here, f of x and y. And that's the function we have. So based on the definition for a continuous or probability function, we have that the function for x will be equal to the integration from minus infinity to infinity f of x and y with respect to what? With respect to x or with respect to y? Correct. So we have to sum or we have to integrate with respect to y when you're looking for the marginal of x. So for this case, we have the integral from, for this one will be easy because the limits are the same, but you need to look at the limits for y. So it's 0 and 1. So 2 over 5 times 2x plus 3y dy. And if you integrate that, you have 2 over 5 times 2xy plus 3 half y squared from y equals 1 and y equals 0. So if you solve this, you get, this is going to be equal to 4xy divided by 5 plus 3 over 5 times y squared from g equals 1 to y equals 0. So this is equal to 4x plus 3 divided by 5. 4x within 0 and 1. We can find also the marginal for y. So in that case, we have h of y will be equal to the integral for this, and that's 0 to 1, 2 over 5 times 2x plus 3y dx. And if you integrate that, you get 2 times 1 plus 3y over 5, and that's for y within 1 and 0. So for the discrete, you sum. For the continuous, you integrate. You can get an expression for the marginal distribution for the continuous case. So if you substitute 0, your x equals 0, your probability is going to be 3 over 5 of having 0. If you substitute 1, probability of having 1 would be 4 times 1 plus 3, so
I think you missed something.
yeah, there's something in there.
We should be three.
Yeah, something. Yeah,
Sorry.
so y1 let's just double check this really quick. So you have 3 over 5. Yeah, there should be an extra term somewhere here. So you have 4x times 1 over 5 plus 3 over 5 minus 4, this is 0, plus see, let me double check. I think you're running out of time here for the exam. So I need to get you the exam back. So I'll double check these and I'll get back to you. This should be less time. Okay. So as I mentioned early in the class, I'm gonna give you the exams back now. The only thing that you're gonna get back is your answer sheet. If you have questions about Any problem, you're gonna have to come see me, and we can discuss the problem, okay?